draw an analogy with these, with these non-locality Bell-type experiments, which were refined over the years and decades to deal with all kinds of loopholes. And so here we want to make sure that we have an experiment that does not have any such loopholes. Okay, so now let me just do a brief review of random circuit sampling and say a little bit about to what extent, what we know about to what extent we achieve this sort of quantum supremacy there. So in a random circuit sampling experiment, you have a quantum circuit, n qubits, depth d, the number of gates is n times d, and then it's of course a noisy quantum circuit, so there's noise on each of the wires, and some constant probability, or some probability. Okay, and just to remind you, the way we think about an RCS experiment is we collect about 2 to the d output samples, so we emission on input all zeros, and then we compute some statistical measure which is called linear cross entropy, which is not efficiently computable. It takes, in general, exponential time, but of course you do the best you can. Now this measure of linear cross entropy is just the expected value of the actual probability of the output with given that you computed it on the ideal quantum circuit, the noise-free quantum circuit. And if you take this expected probability and you normalize it by 1/2 to the n, you subtract off 1, then this linear cross entropy for the uniform distribution is 1, because all these probabilities would be 1/2 to the n. So maybe I shouldn't have put that here. I was already taking the expected value. And for the ideal random quantum circuit, the XCB would be 1. In actual practice, what you see in these experiments is that the XCB value is quite small. And so then we are left with the question of justifying not just whether, so if the XCB value is greater than 0, it sort of gives us some, we want to say it gives us some evidence that the experimental quantum circuit actually implemented the ideal circuit. We also want to be sure that this is really a hard problem for classical computers. Okay, so what kind of evidence do we have that this is hard? So at the time that before the Google experiment, there was this work by Aronson Chen and Aronson Gunn, which gave this justification for random circuit sampling. And the evidence went like this. Well, if your experimental circuit is actually implementing the ideal circuit, then it will often generate heavy outputs which have probability larger than median. And so their hypothesis was that it's very hard to guess whether a given output is heavy or light. Right? So if I give you a random n-bit string, what they're saying is that there's no efficient classical algorithm where you can guess with probability even half plus something exponentially small, that you can get even an exponentially small advantage in n in guessing whether this probability is higher or lower than median. And intuitively, roughly, they were saying the best algorithm we can think of for this problem is the Feynman path integral approach, and that doesn't do any better. What they then showed is that assuming this some slightly more sophisticated version of this hypothesis, QUAF or XQUAF, you can show that it's hard to classically obtain any non-trivial XCD score. for for a perfect quantum circuit, and therefore even for this perfect quantum circuit. And so if you've achieved it in the lab, then it shows that you've achieved quantum supremacy. So this was great. It was a very clean conjecture that showed that this, that you were achieving quantum supremacy. You could sort of say, well, maybe it's a strong conjecture, but at least it's something you can get your hands on. Now, a couple of years ago, there was this paper by Shingao et al. Misha Lukin was on the paper, which refuted X-quark. So what it did was it showed that you can decouple your quantum circuit into isolated subsystems of size that scales with the depth, so that you can incur an error that scales as exponentially minus d, rather than exponentially minus n, as required by X-quark. Now, remember, in all this, d is much smaller than n, and so that was a problem. Okay. Now one could say, well, why not just change our assumptions in X-quark from exponentially minus n to exponentially minus d? The problem is that then that breaks the Aronson-Gunn reduction, showing that in this case, getting any non-trivial estimate of value for linear cross entropy is hard, classically. Okay, so all right, so that was a bit of a setback. There was another development along these lines where, together with Dorit, Arno, Shingao, and others, what we showed is that, in fact, if you assume that your circuits are noisy with constant noise rate, then there's a polynomial time algorithm, classical algorithm, which will output samples from a distribution which is basically indistinguishable from that of the noisy random circuit. And the precise statement, the way to think about this result is that if your experiment collects m samples, then the classical algorithm runs in time polynomial in the number of qubits and n. Now, if you want to think about this asymptotically, then you want to set d equal to log n because d equal to log n is where you get two things happening. One is the output of the noisy quantum circuit is always known to be 2 to the minus d close to uniform. And so if you want to be able to tell the difference between the output of the quantum circuit and the uniform distribution, which is the minimum you have to do, then d cannot be larger than log n. On the other hand, you need log n to achieve anti-concentration. So that's sort of the sort of the Goldilocks regime. Okay, so I said that the intuition behind Aronson-Chen and Aronson-Gunn was that you cannot do much better than Feynman path integral approach. The idea behind the new algorithms is you use, instead of Feynman paths, you use Pauli paths. So you work with a density matrix instead of the standard basis, and then you use a Pauli decomposition. Now this has a few interesting properties. One is that the identity Pauli is special. So this is something you don't get in the Feynman path approach. And and it's also special that noise leaves the identity invariant. And so what you can do is you can neglect the contribution of high weight paths, where weight denotes any non-identity paths. Then you can use combinatorics. So you can show that most low weight paths have zero contribution. And so that further decreases the amount of work you have to do. And you can also efficiently enumerate these non-trivial low-weight paths. And so that's what the algorithm looks like. Okay, so earlier this year, Google did another random circuit sampling experiment, which was larger. It was about 70 qubits with increased gate fidelity. You know, this was for the 2 qubit gates plus the single qubit gates at each iteration. So, but together with that, they pointed out something very interesting. So they said, look, there's a phase transition in random circuit sampling, which works like this. You can think of two different noise phases: the weak noise phase, where you have 1 over n noise, and the strong noise phase, where you have constant noise. And they were sort of saying, well, look, there's a phase transition in terms of global correlations as you go from as you start increasing the noise rate from 1 over n to constant. And in terms of the correlations that you see in the system. So you see global correlations when the noise is small enough, and when it's large, your correlations become small enough that you can achieve, well, should be able to achieve classical spoofing. And so what they're trying to say is that the noise rate is low enough here in their experiments that you should really think of them as 1 over n as opposed to constant noise. This is, of course, it's an interesting point. It's it's something that for small values of n, how do you tell the difference? But still, I think it's a good point. I should say that the practical spoofing algorithms based on tensor network contractions, they've done extremely well. There's this fast tensor network contraction algorithm that they leverage off of. But again, the running time is exponential in the smaller dimension, and it seems like this 70 qubit experiment already poses a more severe challenge to those algorithms. So let me put some of this in context in terms of theoretical work at the very beginnings of quantum computing. So in terms of computer science, we think about the extended Church-Turing thesis, which sort of is the foundations of computer science. It says that any reasonable model of computation can be simulated on, well, at that time, a probabilistic Turing machine with utmost polynomial simulation overhead. This is validated by quantum computers, and that's the whole point of quantum computation. But the early demonstration of this was, had it was not nearly as robust. So to show this, one had to show three things. That you can efficiently program quantum computers, that they are digital, and this was shown only with respect to 1 over poly n errors, right? And then also that you can get super polynomial speedups on some challenge problem, not necessarily useful, and that was some sort of Fourier sampling problem. Okay, so you could think of that as phase 1 of this violation of the extended Church-Turing thesis. In this phase 2, the speedup became much more robust. It was Shor's algorithm for factoring and discrete log. And the digital nature became much more robust. So that was fault-tolerant quantum computation with constant noise error, which was again, this showed that you could go much beyond that. So in this sense, you could say that these quantum supremacy experiments, maybe they fall squarely in this phase 1 of an experimental violation of this extended Church-Turing thesis. And ideally, what we'll do is be able to show it, establish it already in phase one. But if, as Misha says, the era of fault tolerance may be much closer than we think, then possibly we are ready to move on to early fault tolerance. Okay, but we should use every trick we can to get there. Okay, so now this paper about the phase transition in RCS between weak and strong noise, we can use it we can think of it as giving us some hope that spoofing strategies would not work in the weak noise regime. On the other hand, our proof techniques for classical hardness appear to break down in this weak noise regime. So it's really an open question whether there's any kind of formal evidence we can give for computational hardness of RCS in this weak noise regime. For example, is there any variant of X squared that is consistent with, that with all these known classical spoofing algorithms, but which implies hardness of XCD spoofing for RCS? So we don't know how to do that. Okay, so let me just finish up with a couple of more points of discussion. So there are other things we can do in terms of quantum supremacy. There are the so-called cryptographic proofs of quantumness, which are based on post-quantum cryptography. So the classical verifier knows the secret key for this post-quantum cryptography, and therefore can use that to test the quantum computer. So there are two advantages of this. One is classical hardness is now provable and based on standard crypto assumptions. The second is the verifier is now efficient. There's this challenge that that we've been working on and off. Can we formulate a concrete quantum supremacy challenge based on these kinds of schemes for the next generation of NIST devices? So meaning 1,000 qubits, 99, maybe 4 nines of gate fidelity. So we've managed to do this. We've managed to do this in a way that achieves these goals and is correct. But unfortunately, when we achieve these goals, we soon realized that our implementations were not correct. And when they were correct, they didn't really implement these goals. So we're still trying to see if we can actually achieve this with a protocol which you cannot break classically. One last question one can ask is it even reasonable to ask for scalable separation in the presence of constant noise? So, meaning, for example, with n qubits, a log n depth random circuit sampling problem, it gives us a detectable signal even in the presence of constant noise, right? Unfortunately, for RCS, you can spoof this classically. But that doesn't mean there isn't some other computational problem that you could do on a noisy random circuit with log n depth, constant noise, for which there's probably no classical spoofing strategy. That would be great, because then that would give us a scalable way of achieving quantum supremacy, even on a completely noisy, non-error corrected quantum computer. So I conjecture that, in fact, for these cryptographic proofs of quantumness, at least there's an information theoretic verification scheme, meaning exponential time classical verification, but provably no classical spoofing. And we could even ask whether there's a way to do this where the classical verification scheme is efficient. And I'm not sure which way to speculate on that. if forced to, I would say that I think the answer to this may well be yes. That's what I would conjecture, but not nearly as robustly as the first one. Okay, thank you.
Thanks very much. So we have time for a couple of questions. Please just hold out to the mics if you have a question. And maybe I can just start out with a question. So, you started out by talking about sort of, how you think we should define this term quantum supremacy, and if I understand correctly, that we should have a pretty high standard for the kind of, classical difficulty of these problems. That seems like a pretty hard thing to achieve, because I guess at least the problems that we've been using to kind of try to establish this, they're not things that have been studied for a long time. You talked about these conjectures, which have been, proposed and maybe falling. So, is this a realistic thing to maybe have quantum supremacy with this kind of very strong notion of classical arguments?
Yeah. So that's a good point. I think that maybe there are two ways I'd answer that. One is that there is a there is a prospect of I think it's not out of question that there's going to be some way of doing achieving this based on either cryptographic proofs or some variant on not IKP because all that's broken, but there are other schemes where you could base it on some sort of measurement-based schemes, etc. But then there's another thing I would say, which is that we could imagine that we were in a different world where there wasn't an alternate to Feynman path integrals, and this export conjecture seemed to hold up for a while. I would think of that as a reasonable level of a reasonable guarantee, right? Let's say, this is what we do in cryptography as well. We formulate a very precise conjecture, go at it for some time, and then if it survives that, that's evidence. And so the important thing in this methodology is that there's something precisely stated that everybody can take a go at. And,
Yeah, great. Michael?
Yeah, so the space transition in XCD, I guess the way we sort of understand it maybe more precisely is it's the ability of fidelity, or XCD to estimate fidelity. So can you just, fidelity is a very sort of quantum comment on how you think of that.
Yeah, so I don't know if I have any special intuition about that particular correspondence. I do think that there's something about RCS and which is interesting, which is that the one thing about RCS is that it's spreading, that it's spreading correlations very fast throughout the circuit, and so so there's that competing with noise, and I think that this particular competition and how that competes with classical computation complexity. I think this is the thing that I don't understand too well, and I think that's what's the core thing to. I feel that's the basic thing to put up in the.
Okay, great. Let's thank Umesh for a great talk.